How we feeling? We understand filters? First order, second order, you guys got it all, right? Let me summarize what I think you learned on Friday. I went to this awesome meeting on Friday. I learned how they're paying for all that stuff outside.
What do they make? You know?
A whole building. It's going to be... What's that? Sort of. It's going to like touch this building, but I don't know that... I think you're going to have to go outside to get to the new building. But it's basically going to be between this building and Gladfelter. And it's a... Science and research. It was originally going to be an engineering building, like 3 years ago, and then I don't know what happened. Somehow we got negotiated out of that, and now it's just going to be a science and research building. So it's possible that there may be some engineers in there, but you know, not really.
Engineers.
What's that?
Because of few engineers.
Because of a few engineers?
Yeah.
What do you mean?
It's like there's enough skill, like.
Yeah. Oh
compared to
no.
other places.
We're going to get a new building eventually, just not that one. Next year, I think, spring of 2015 maybe? No, spring of 2014, I'm sorry. They also talk about the dorm that's going up on CB Moore and Broad. That's going to be done like pretty soon apparently, like in time for the fall maybe? Yeah. What? Do you really? I'll go live there. All right. Do they let kids go? I mean, I'll take my whole family. All right. Okay, so today we're going to kind of, we're sort of nearing the end of a unit. I don't like the word unit. It sounds like we're in high school, but, you know, it's like a logical chunk of information that all fits together in a certain way. So it's on. Is it caught? Yeah, it's on. Basically what we've done is we've learned the basics of making filters, right? So just to kind of summarize where I think you should be. For a low-pass filter circuit, we've learned learned how to do AC analysis, and the AC analysis has taught us a couple things. We learned how to do a first-order low-pass filter. And remember, a low-pass first-order filter looked like 1 over j omega RC plus 1. Is that right? And it was first-order because there's only one energy storage element in it. All right. And remember, there was the cutoff frequency is set by the time constant tau. So we learned that in that case, there was a cutoff frequency that was equal to 1 over tau, which for an RC circuit is 1 over RC. All right? And then we also learned about second-order systems, which have two energy storage elements in them, right? So an energy storage element is a capacitor or an inductor. It could be two capacitors, it could be a capacitor and an inductor, two inductors, whatever. But the point is you build it and you get a second-order system. Does anybody remember the transfer function of a second-order system? Do you have that written down? We've only looked at it like 10 times, right? S squared plus, there we go. Yeah, we're going to do all that nonsense again. 2 zeta omega naught S plus omega naught squared. So just a couple things just to make sure we're all on the same page. How come there's an S down here but not up here? So turns out S is really, for the purposes, it's actually a little bit more sophisticated than what I'm about to say, but for the purposes of this class, S is really just shorthand for j omega. Again, there's a little bit more going on than just a simple substitution, but to keep life simple and interesting for the time being. This lecture is gonna get ugly enough as it is. You can just replace your j omegas with an s. Okay. So you have this property, and
It's not omega square over S square plus.
I'm sorry.
It's not for second order. It's not omega square over.
Well, that's if you take the magnitude of this. Remember, for both of these functions, you can take the magnitude and the phase to figure out the. So there's sort of like two things going on. You can get the when you calculate the phasor expression that relates input and output, you get what's essentially a complex function. Like this is a complex function. But then that we learn, for that complex function, you can take its magnitude and you can take its phase. And the magnitude and the phase are what tell you how to take a cosine, an input cosine, and like what the output cosine is. So for example, for this function, the magnitude was 1 over, let's see, it was omega RC squared plus 1 square root, right? And then there was a phase expression as well. So we can do the same for this guy, right? What was the magnitude for the second order system? But this isn't right. There's no way this equation's right. Isn't there a omega naught upstairs?
Yeah, that's
Oh. Oh, that's what you were asking about. Okay, I beg your pardon. Yeah. Good. Well, now that we're here, what was it? So the magnitude of my second order system should have been omega naught squared times, let's see, omega naught squared minus omega squared. Omega squared plus, I don't think this is how we did it in class before, is it? We didn't do it in terms of zetas and omega naughts. We did it in terms of R over L. Okay, well let's actually just do that one out longhand then, just so we're all on the same page. So if we express our generic, so the R and the L is correct, but that's sort of like specific to that circuit. What's nice in some way about expressing your transfer functions like this is that it's generic. So once you do this analysis on the generic function, then if I give you any circuit, all you got to do is just figure out what's omega naught, what's zeta, and then that's it. You don't have to do all that ugly math anymore. You just plug those values into the final answer. So what is my magnitude? So what is the magnitude of the transfer function for my second order system? It's going to be my numerator, which is omega naught squared. And then, let's see, what's the magnitude of my denominator? Keeping in mind that s squared is really j omega squared, and j omega squared is really minus omega squared, right? This is really j omega squared, which is minus omega squared, right? Because j times j is -1. So I've got my real part squared, which is, my real part is omega naught squared minus omega squared. There's my real part squared, plus I've got my imaginary part, which is 2 zeta omega naught j omega, right? So it's 2 zeta omega naught omega. All of that's my imaginary part squared, and that's that whole mess square rooted. Wow! What a mess. But we did an example of this with the RLC circuit, and you should have gotten essentially the same thing, except that we subbed in individual values like R over L and whatever zeta was for these values. Okay, but it's essentially the same thing. So we got a magnitude, we got a phase. And what did you discover? What did you and Elliot talk about in class on Friday with respect to this circuit? Is a low-pass filter? What's the cutoff frequency? The natural frequency? Sort of. Doesn't it depend? Does it depend on zeta? Elliot did come here, right?
Oh, yeah.
Yeah, I mean, He told me he came. He gave me. He said there was a lot of head nodding. Right. Okay. So what's the deal with zeta? How does zeta affect the cutoff frequency? Good. So this case is a little bit tricky. So with the second order case, with the second order system, you have two cases. Your system can either be underdamped, or it can be overdamped. What values of zeta imply an underdamped system? Good. So zeta, that's actually the definition of underdamped. If zeta is between 0 and 1, you have an underdamped system. An underdamped system means that the step response oscillates. What about an overdamped system? What's my values of zeta for an overdamped system? Zeta greater than 1. What does my step response look like for an overdamped system? Right, just sort of like that. Okay, there's your step response. Okay, so what you should have done in class on Friday was to talk about not the step responses, but the transfer functions. Okay, so the way I was told it was going to happen, or rather the way I told Elliot it was going to happen, was that you were going to take this function, okay, or its equivalent version for an RLC circuit, and you were going to plug in some values for RL and C, okay, and then you were going to plot this function, the magnitude, versus frequency, and see what you see, okay? And what you should have found is that what this plot looks like varies on the value of zeta. For an underdamped system, when you created your plot of magnitude of transfer function versus frequency, what you should have found is that at low frequencies you have a gain of 0 dB. Right, it's a gain of 1. And at high frequencies, it rolled off. And what happened in the middle? Anybody remember? You get a little bump. You get a whoop. A resonant peak. Right, that's a 10-cent word. Resonant peak. Okay. And what frequency was that resonant peak roughly about? The cutoff frequency, which was about in the neighborhood of omega naught. Which shouldn't surprise us, because what's the frequency of oscillation of this step response? Omega naught, right? Remember we studied the frequency that this thing oscillates at? And we said, hey, it oscillates at omega naught. What that's trying to tell you is that in this configuration, this circuit has some natural tendency to oscillate at that frequency. So guess what? If you come along and you drive the circuit, if you drive the circuit with a cosine at that frequency, that same frequency that the system is already tuned, it's already like primed. That's its sweet spot. Okay? So you know it's its sweet spot because if you give it just a step input, it still oscillates at that frequency. So if you now come along and give it a cosine input at that same frequency, it actually resonates, right? The output gets bigger than the input. It's kind of cool. So it shouldn't surprise us that you get a resonant peak at roughly the neighborhood of omega naught, and then after that your system rolls off. Okay, so you get a cutoff frequency that's at about omega naught, and then after that your system rolls off. Okay, so now you're getting your low pass. What happens for your overdamped system? Is it the same thing? Any takers?
It is for a part of it,
Yeah.
and then it goes to the root.
Good. So, for the underdamped system, what property did my roots have? The roots of the characteristic equation. Real or complex? Complex. So the underdamped system had, well, remember we took the characteristic equation, which is basically just the denominator. when you solve for the roots of the characteristic equation, so let's see, roots of characteristic equation are complex. In this case, the roots of the characteristic equation were real. So that was another fundamental difference. So you got all these differences, right? There's values of zeta are different between overdamped and underdamped. The step response is different between overdamped and underdamped. The quality of the roots is different, real versus complex. And then, so the last piece we need to figure out is what goes on here. Like, what does the low-pass filter characteristic look like? So let's say I solve my characteristic equation for some particular circuit, and I find out that I have two roots. So let's say I solve my characteristic equation and I get those values. Yes, sir?
Is that W not or omega not half of that?
Yeah, this is roughly. Yeah, it's right. It's like not exactly, but it's close enough. So suppose I solve my characteristic equation and I got these two real roots. What would my transfer function look like? Am I going to get something that looks like this? Definitely not. You only get this resonant peak with an underdamped system. So it's a low-pass filter. So I know for sure I'm going to start with a low pass. Yes?
That top one also W to the not or the bottom?
What are you talking about? Oh, sorry, this is just W. Yeah, I beg your pardon. Now what happens? Drops? How steep? Real steep? 20 dB per decade. Did Elliot tell you what that was? He's stealing all my thunder. Okay, what frequency does stuff change at? Let's start with that. Is it omega naught? No, it's not. So, omega naught is only the cutoff frequency. That's only the cutoff frequency for an underdamped system. For an overdamped system, it should have worked out differently when you did your little Excel example. For an overdamped system, it was no longer omega naught that set the cutoff frequency of the system. It's the roots of the characteristic equation. So if I solve my cutoff frequency, my characteristic equation, and I got those values, my first breakpoint would be at 1,000 radians per second, right? Whichever the smaller one is, and then the system would be with like a low-pass filter, and then I get to my second pole, which is at 10,000 radians per second. And it's still a low-pass filter, but now it's going to be a steeper low-pass filter. Okay, so yes.
Yeah, the roots are just another name for poles.
Yes. The roots exact. Poles, by definition, are just values of S that make your denominator 0. Exactly. So it's kind of like this cool thing where, I mean, we got the characteristic equation originally by messing with the differential equation, right? It was like the coefficients of the differential equation. That's how we got our characteristic equation that we were solving to figure out zeta and omega naught. But now what we're finding is that even when you get the transfer function, it's basically just the poles. It's the values of S that make your denominator 0. Okay, so what does all this mean? So let me try to superimpose these plots on top of each other. If we had a first order low pass filter, so let's say we have so let's say that circuit number 1 is a first order low pass filter with a cutoff frequency of, should we say, 1,000 radians per second? Okay, so can someone tell me, so if that's the case, then this is going to be 1,000. What's the transfer function going to be for my first order low pass filter with a cutoff frequency of 1,000? Yeah, so 1 over. Somebody said it. 1 over. So in this case, it's h of omega equals. What's always the transfer function for a first order low pass filter? 1 over j omega RC plus 1. Okay. So 1 over j omega, something I don't know yet, plus 1. So how do I get to something that I don't know yet? Yeah, we've already done it essentially, right? I mean, you could solve it for 0.707, but we've essentially already done that, right? We've already figured out that for a first order low pass filter, the cutoff frequency is 1 over RC. So in this case, if my cutoff frequency is 1,000, so 1 over RC is 1,000, so therefore my time constant RC, 0.001, right? 1 over 1,000. So there you go. So let's say, I don't know, what do you want to say? 0.001 j omega. Okay. So this is try to make things better and I make them worse. Okay. So this is what number up here? What's the value of this transfer function at low frequencies? You can ask me one of two ways. It's a gain of 1, or equivalently, that's a gain of 0 dB. Because if you take 1 and take 20 times log base 10 of 1, you get 0. Good. What's my value at the cutoff frequency? Let me try to make that a little bit more. What's the value of this function at the cutoff frequency? Right. The gain at the cutoff frequency is 0.707. All right? But if you take 20 log base 10 of 0.707, so in other words, if you take your 0.707 and convert it to decibels, you always get negative 3 dB. So this is negative 3 dB. Okay.
What was it again?
At the cutoff frequency, right, so at the cutoff frequency, the magnitude, by definition, is root 2 over 2, 0.707. If you convert that to decibels, if you take 20 log base 10 of root 2 over 2, push that into your calculator, you always get negative 3 decibels. So much so that we often call the cutoff frequency the 3 dB point. We don't say the minus 3 dB point. Don't ask me why. Probably because we're lazy and the minus is assumed. Laziness is a beautiful thing. It makes engineers efficient. So don't, you have to embrace your laziness. That doesn't mean be like slovenly. Okay, so that's a first order system. So now I want to compare this to a second order low pass filter. Now, would you like to make this a overdamped or an underdamped? We're going to do both. Which should we start with? Let's do under. I think under is a little bit better behaved. Okay. So what should be the two roots of my and I want to make it roughly equivalent to this circuit. So S1 and S2. So how about I make my first root of the characteristic equation be minus 1,000, right? Same as my current one. Okay. What about, I need another root. It's got to be bigger than 1,000. Yeah, okay. Why not? Let's live dangerously, right? So let's make the second root at 10K. So my first question is, actually no, my first question is, what's the plot going to look like? So at low frequencies, I'm going to have a gain of 0 dB, because it's a low pass filter. So at low frequencies, I better be passing my signal rather. Then when I get to my first frequency, it's going to start rolling off. So now I'm going to start rejecting my signal exactly the same way as before. And then when I get to 10,000, it's going to be a steeper drop-off. See how that works? So in this phase, they're both passing the system, so they both give me the same response. In this phase, both the first and second order circuit are giving me the same response. And the reason is that you can think of the second order circuit as having two poles, okay? But at these intermediate frequencies, only one of those poles has been activated. Therefore, since only one pole has been activated, that's exactly the same as a first order system in which one pole is activated. So that's why they're giving you the same roll-off. But then, when you get to 10,000, now you hit the second pole. Now the second pole activates on the second order system, and you get a steeper roll-off. Okay, so that's giving you more rejection, right? That's doing a better job of rejecting high frequencies. Yes. Yeah, I mean, we've just redrawn this basically. We just superimposed the first order system on top of it to show you the difference. Yes, sir.
Like the first pole is always going to be, it's going to cut off negative 3 dB.
Yeah.
For the second pole, so it's going to cut off that.
So it's kind of interesting. The way it would work for the second pole is that, let me try to do this a little bit more cleanly. Whatever this number is 3 dB less. Right? This difference is 3 dB. Except now I've made my picture an unholy mess. Hold on, let me see if I can clean this puppy up. What's that? 0.707. That's just how poles work. Each pole like multiplies your system again by 0.707 at the cutoff frequency, and each 0.707 is a 3 dB drop. Yes, sir.
What if S1 is equal to S2? What if S1 is equal to S2?
Equal to S2. Then that's the special case called the it's not overdamped and it's not underdamped. It's critically damped. And in that case, you wind up at that frequency, it would be 6 dB down. You'd get 3 dB from the first pole and 3 dB from the second pole. So let's say S1 was 1,000 and S2 was 1,000. Then at 1,000, instead of being 3 decibels down, you'd actually be 6 decibels down. It would still be a low-pass filter. It's just that at the cutoff frequency, you would be 0.707 from the first pole times 0.707 from the second pole, which would be negative 6 dB.
Would that decay at 40 decibels?
And it would decay at 40 decibels. Okay, so we haven't really talked about, did Elliot calculate for you where this slope comes from? Like how, I know we were throwing around this minus 20 dB per decade thing. We haven't really talked about it in a ton of details. Anybody, did he get into that? A little bit? I actually don't want to get into it, at least not right now. So all I really care is that you notice that adding more poles makes it steeper, and steeper means more rejection. If you can sort of work with that, then I can work with that.
So, but just on that same note, it's always after the second pole or after the second transition, that's 40 dB?
40
So
dB.
always?
The slope, for what it's worth, every pole reduces the slope by 20 decibels per decade. Okay, so this one is rolling off at 20 dB per decade because there's only been one pole. This one is rolling off at 40 dB per decade. Okay, and all that means is, if, like, see how I've drawn this as a line? So that means that, okay, this frequency is 10K. If you go 1 decade out, a decade is a factor of 10. So what would be 1 decade forward from 10K? That's like a factor of 10. It'd be 100K, right? 100K is 10 times more 10K, so that's 1 decade. So what this is telling you is that in 1 decade, you're going to expect to drop by 40 decibels. Every time you multiply frequency by 10, you go down by 40 decibels. Whatever. I really don't want to get into it now. I'll leave that for signals. We'll do that in signals till smoke comes out of your ears. Yeah?
What effect that is? What about the zeros? What effect do they have on the graph?
Oh, we didn't get to zeros yet. So poles decrease your slope by 20 dB per decade. Zeros increase your slope by 20 dB per decade. So, for example, again, I don't want to get too much into this because we'll do a whole different lecture on this. But suppose you had, you could have a system where you have a gain of 0, and then so here you'd have a 0, and then you'd have a pole, and then you'd have a 0. That's a bandpass filter, right? So that's what it does. So this would be a 0, this would be 1 pole, and this would be another pole. You can make yourself a bandpass filter. So zeros make it go up, poles make it go down. All right, you've got mail. Okay, let's get the transfer function of this overdamped second order system. So I want to get my transfer function for my overdamped second order with S1 equals 10K minus 10K and S2 equals minus 100K. Is that what we said? Oh no, we did 1K and 10K. I beg your pardon. How are we going to do that? I mean, I gotta take this information and makes it look like this. Totally. Yeah. So we know that if we take this equation, this denominator, and solve for and set it equal to 0, the roots that we'll get should be those two numbers, right? That's what that means. So why can't we just work it backwards? Why can't we just say that my denominator is really S plus 1,000 times S plus 10,000? Can that be my denominator? Totally, right? Because what's one of the roots of this denominator? What's a value of S that makes this denominator equal to 0? What value of S makes this term equal to 0? Negative 1,000. What value of S makes this term equal to 0? Negative 10,000. So this is my denominator. Pretty sweet, right? So putting all that together, so basically, and then I need something in the numerator as well. I need omega naught squared. So we'll fill in my numerator in a second. So why don't we start by foiling my denominator? So my denominator is going to be S squared plus 11,000. 11,000 S plus for 10 million, right? Because this is 10 to the 4, and that's 10 to the 3, so that better give me 10 to the 7. What goes in the numerator?
10 to the 7.
Right, it better be whatever this term is. 10 to the 7. So there you go, there's my transfer function. 22,000? No, it should just be 10,000 plus 1,000, 11,000. Am I misunderstanding? Oh, I know where you're getting with this. Okay, so this is my transfer function. If I give you this transfer function and I say, plot me the low-pass filter, you get this, right? Because all you do is find the pole frequencies, which you get by factoring your denominator. When you factor your denominator, you're going to get minus 1,000 and minus 10,000, and that gives you this transfer function. What's my value of omega naught for this circuit? Square root of 10 to the 7th, right? Because it's always, where is it? It's always the square root of my constant term. So that's going to be the square root of 10 to the 7th, which is, let's see, 10, it's root 10 times 1,000. Root 10 is 3 and change times 1,000, 3 something, right? 3,000?
3,126.
3 times, sorry.
3,126.
3 times 10. Oh, I see. Okay, okay. Yeah, that's exactly right. So like 3.16 K rads per second. Fun! What's my value of zeta? How will I know if my value of zeta is wrong? If it comes out less than 1 or negative, right? The only correct answer here had better be a positive number bigger than 1. So what am I going to do? I know that 2 zeta omega naught equals 11,000, and I know omega naught equals root 10 to the 7th. So let's actually get a number. All right, it's going to be 11,000 over 2 root 10 to the 7th. 1.7? Can I get a confirmation on 1.7? Oh, I got some hot debate here. Someone's saying 1.6. No, I'll get my calculator out. You guys look busy. 11E3 divided by 2 divided by 1E7 root divide. I'm getting 1.74. Yes, sir. Oh, you're good? You give me the thumbs up? Hey, isn't that neat how it all worked out? Right? So here's an example of a system where it's second order. It's got poles where we figured out, we started from the poles. We used that to get the transfer function. The transfer function gave us an omega naught that we expected and a zeta that made sense. Okay? That's pretty good. This is usually how people design filters. They don't start with the resistors and the capacitors. They actually start with the equation. They say, I need a filter that has these properties. It's got to cut off at this frequency like this and that frequency like that. Then they design it, and they say, okay, now I need a circuit that does that. Okay, so that's why today we're just messing with equations, right? We can always come back later and say, sweet, how do I actually make that filter? Okay, so now, for comparison, we're going to make ourselves a underdamped second order low-pass filter. Now we've got some decisions to make. So now I want a underdamped no. Yes, underdamped second order low-pass filter. Now remember, for a second-order system, I'm going to have complex poles. So I can no longer just come here and say 1,000, 10,000, that's my breakpoints. Where's the cutoff frequency going to be? Roughly at omega naught. I say roughly because there's like a little correction factor, but roughly at omega naught. So where do I want my omega naught to be in this case, if I want it to look roughly like this? Yeah, so let's pick it so that in this case, omega naught is, let's just say, 1,000. I like it. Okay, need a value of zeta. Less than what's that?
Less than 1.
Less than 1. So give me a value that might work. 0.5. Okay. Good. So we can get the transfer function for that, right? The transfer function now is actually just, it's pretty easy. We don't even have to do anything, right? We just plug and chug. It's going to be omega naught squared, so that's 1,000,000, over s squared plus 2 times zeta, that's nice. 2 times 1/2 is 1, times omega naught, 1,000 s, plus 10 to the 6. If I were to take my roots, what would I get? If I were to take the roots of my denominator, my poles, real or complex, we're not sure.
Should be complex.
Better be complex, right? It's an underdamped system. Let's actually get those poles just so we're all on the same page. I'm going to fire up MATLAB. Let's see here. You are not going to believe this. So I'm getting that my roots are s equals minus 500 plus or minus j times 866. Okay, are they complex conjugates? Yes. All right. Remember, complex conjugate means same real part, opposite imaginary part. Are they in the left-hand plane? Does everybody remember what left-hand plane means? Did we talk about that? Yeah. So remember we said if you can imagine your complex plane, your poles should all, if I were to plot these, they'd be at negative 500 plus 866 and negative 500 minus 866. But they are in the left half, okay? Their real part is negative. That will always be the case for a stable system. Wait till you get to controls. You will live and die by that rule, okay? Do you know what's interesting about this? I've expressed this in rectangular form, have I not? Let me express this for you in polar form. I can do that, right? I can take those poles and convert them to polar form. You're not going to believe this. I get 1,000 1,000, let's say, angle plus or minus I'll do it in degrees, even though I usually despise that. Plus or minus 120 degrees. This is also interesting. What's the relevance of the 1,000? Omega naught. Not an accident. Pretty tight, huh? See this? That will always be omega naught. What's the relevance of the 120? Let's see. This is 0, 90, 180. So where does 120 lie? If this is 90 and this is 180, where's 120? It's, let's see, it's 50 degrees past, no, 30 degrees past this and 60 degrees up from here. So it's about here. So my poles are really about right there. Good. Turns out, if I make zeta closer to 0, my poles will still travel on, they'll just be like, they'll go in that direction. That's if zeta gets smaller. Let's not sweat too much about that. Okay, transfer function time. So I plot my transfer function for this system. What's it going to look like? At low frequencies, I'm going to have 0. And then at 1,000, I'm going to have little peak. And then what happens? It rolls off. At what slope? Is it going to roll off at the 1-pole slope or the 2-pole slope? The 2-pole slope. Because I'm effectively taking both poles at the same time. Right? I'm effectively getting both poles at omega equals 1,000. Right? So instead of having an initial roll-off of 20 dB, an initial 1-pole roll-off, and then you pick up a second pole, you pick up both poles at the same time. So you see how these two lines are parallel? They're parallel because they're both rolling off with the same slope. Okay? Both of them have the 40 dB per decade roll-off that's characteristic of the two-pole filter. All right. How would my underdamped second-order low-pass filter change if I took this zeta and instead of a half, I made it 0.1, but I left omega off the same? How would my poles be different? Angle. What about the magnitude? Same magnitude. Okay, so in other words, all the action is still going to happen at 1,000, but the angle will change. This number will get closer to 90. And in doing so, these poles are essentially going to get closer to the right half plane, which makes your system closer to being unstable. Right? That peak gets even peakier. Pretty crazy. Okay, so that's it. You've consumed filtering 101. So here's the moral of the story. I've got 3 minutes left, but I have an important point to make in these 3 minutes. You've learned how to make a first-order system. Okay? So a first-order system gives you a single pole. That single pole can, you can make an RC circuit to make that. You can put that pole anywhere you want by picking the value of R and C. You've learned to make a second-order system. Again, that second-order system can either be overdamped or underdamped, and you can pick the properties of your low-pass filter by placing your poles in a clever location. Right? You can put the cutoff frequency where you want. You can make the roll-off how you want, so on and so forth. And if we just had a filter, if we had a circuit that could give us these, that could let us place these poles, we'd be good to go. We're going to look at that on Wednesday. Now, here's the last question. What if a second-order system isn't enough? Right? What if you find yourself in a situation like this system is pretty good, but what if I'm not rejecting high frequencies fast enough? Right? What if I need a system that cuts off like that? Okay? What if I really cannot tolerate having anything at all after 1,000 hertz or 1,000 radians per second? Second order system's not going to do it. What if I need a third order system or a fourth order system? What do I do? Daisy chain them, right? If you take a second order system and then put another second order system after it, guess what you got? Fourth order system. If you know how to analyze a first order system, if you know how to analyze one second order system, and you know how to analyze another second order system, you know how to analyze a fourth order system, right? You can put as many of these in a row as you want, right? 2 second orders, a fourth order, a third, whatever. Just daisy chain them together, and you can start to think about how their frequency characteristics arise, okay? In fact, we'll probably start class on Wednesday. I'll show you a circuit that I built a couple years ago, which I think wound up having like 6 or 7 poles. But it's easy to analyze because once you understand how each component works, you just daisy chain them together and you understand how the whole system works. It's pretty elegant. Okay. Thank you.